Rustin. Today we will talk about TiCDC. It's a tool for replicating the incremental data of TiDB. First, let me introduce myself. I'm Rustin. Of course, I'm Pinkapper, and I'm working on the data replication team. I'm also a committer of TiDB migration team and a reviewer of the TiKV team. You can reach me on GitHub, Twitter, and my personal website. Of course, you can find me on Slack. Today, we will talk about architecture of TiCDC and some key metrics. And I'll also answer some frequently asked questions about TiCDC. At last, we will have a Q&A session. So if you have any question, please feel free to ask in the Q&A session. And before we talk about TiCDC, we have to know what CDC is first. The full name of CDC is change data capture. In TiDB, there are some scenarios we need a CDC to capture the data from TiDB and send it to other system, like like a Kafka or other TiDB cluster. The first scenario is a data disaster recovery. As you can see, we can fetch the data from one TiDB cluster and replicate the data to another cluster. So some disaster happens, we can just switch our application to use the downstream TiDB cluster. Also, we can store the data in S3 and we can recover the data from it. There are some requirements for this scenario because we want our downstream more useful. Like we can send some read traffic to the downstream cluster. So we need to make sure the data is consistent. There are some level of consistency. The first one is no requirement. It means we don't care about the data consistency. We just want the data as soon as possible. You can send it randomly to the downstream. The second one is a snapshot consistency. It means we can make sure the data is consistent at a specific point in time. In TiCDC, we have a function called sync point to support it. You can choose a specific timestamp and use TiDB's stale read feature to read the data at that timestamp. The second one is the eventually consistency. It means we can make sure the data is consistent after a period of time. In TiCDC, we have a function called redo log to support it. After the disaster happens, we can just reply the redo log to the downstream TiDB cluster, and we can have a consistent downstream. And in this scenario, we need to focus on two performance indicators. The first one is RPO, aka recover point objective. It means how long we can tolerate the data loss. In most cases, we can guarantee the RPO is less than 10 seconds. It means at most 10 seconds of data loss. The second one is RTO, recover time objective. It means how long we can recover the cluster to the normal state. In most cases, TiCDC can recover it in 5 minutes. And the second scenario is the data integration. As you can see, we can fetch the data from one TiDB cluster and replicate the data to another system. Like it can be Kafka or S3 or other system, not only a database. We can convert the change data to different formats, not only a bunch of key value. For example, we can change the data to Kafka message. We can use the Canary JSON and Arrow to encode the data. We can also store the data in S3, and we use the CSV to encode it. It's very common. It's very common in database. In this scenario, we also need to focus on two performance indicators. The first one is the throughput. It means how many data we can replicate per second to the downstream. The second one is latency. It means how big the lag is between the upstream and downstream system. Some users really care about the latency because they want the data is as fresh as possible. Now, you know why we need a TiCDC. Let's talk about TiCDC. It's for TiDB. We'll take a look at the architecture of the TiCDC. You know, TiCDC is a distributed cluster. We call each TiCDC instance a capture. Each capture can have multiple roles to process the data. You can imagine this whole picture as a capture, as an instance of a TiCDC cluster. We can see there are two types of roles. One is the owner, this one, and the other one is a processor, this one. So it's just a logic concept, not a physical concept, because in physical we only have one instance called capture. You can imagine this is this whole picture is as a capture. And you can only have one owner in TiCDC cluster, but you can have multiple processor in your capture, of course, in your CDC cluster. The owner is responsible for scaling the tables and executing the DDL. Because the DDL is a special option, you can't execute the DDL multiple times. So we need to make sure the DDL is executed only once. And that's why we need the owner to execute it. We only execute the DDL in owner. The processor is responsible for replicating data for change feed. Each processor can only process one change feed, and a change feed can replicate multiple tables. You can see there is one processor, and this processor for this change feed called change feed 1, and this change feed has two table pipeline for table 1 and table 2. Maybe you have a question, what is a change feed? You can think it's just a configuration for some tables. User can write a configuration file to describe the change feed, like this one. And then TiCDC will replicate the data for those tables in change feed configuration. For example, change feed 1 have two tables, so we can replicate the data for those tables. We can see there are multiple pipelines in your processor. It's only for one table, and actually in each table, each pipeline, it has 4 components. The first one is a puller. It's responsible for pulling data from TiKV, and the second one is a sorter. It's responsible for sorting the data because we receive the data randomly. And the third one is the mounter. It's responsible for decoding the data because we received a bunch of raw KV. We can't just send it to downstream. And the last one is a sink. It's responsible for send the data to downstream, like MySQL or Kafka. As you can see, the core of TiCDC is a table pipeline. So let's take a deeper look at the table pipeline. The table pipeline looks like just like a pipe. So it's very simple and straightforward. The data flows from puller to the sorter, and then to the mounter, and finally to the sink. We can send it to downstream. We can go through the pipeline step by step and see how it replicates data. This is an example. We can create a table named test. It has 2 columns. The first one is name. It's a primary key. You can see it's a primary key. The second one is age. It's just an integer. We insert a row into the table, and then we update that row so we can trace the data flow in the table pipeline. But before that, let's check the real data structure in TiKV because we get data from TiKV. By the way, those two DMLs are executed in different translation, so it's in different time. For the insert statement, we can see the key is the test jack. The value is jack and 20. The key is the table name and the primary key. For the update statement, we can see the key is still test jack, but the value is the jack and 25. So we can see the value is updated. This is just a simple example. In fact, TiKV use a more complex key value structure, especially for the key. It's very complex. But it's not important for this talk, so we can ignore it. We can just think TiCDC get some data like this key value from the TiKV. The first node is puller. Let's suppose we have two regions. The first one is region 1, and it stores the data of the first row. The second one is region 2, and it stores the data of second row. You can see this is a test Mac. This is test jack. So it sounds a little bit stupid, but it's just for the example. So it's okay. This is one row. This is one row, and puller will put the data from TiKV, and then it will send the data to the next node called sorter. As you can see, the real row change data has some extra information, not just the key and value. The first one and the second one is start TS and commit TS, and we can see it's already committed because we execute those DML in TiDB before we pull the data, and both of them are put option because one is the insert and one is the update, so it's put. Then we can see the key and value. They are also an old value. It's the old value before the update. Like for the update statement, you can see the old value is jack and 20. Sometimes we need it. Like users want to know the old value before the update, so we can just keep it and send it to the downstream. And the sorter, the second node, is a very important component because we receive the data from different regions. So the data is not in order. We need to sort the data by the community TS for one table, because we have to keep some consistency. For example, we can't update the data before the insert, so we can't just send the region 2 before we send the region 1's data. As you can see, we merge the data from region 1 and region 2, and then sort the data by community TS. You can see here. Also, we can see the resolve event. It's a special event. It means the data before this event is sent to the TiCDC. No more data will be sent to the TiCDC, which has a smaller community TS than this event. This kind of event like a watermark. It's a very common pattern in the stream processing system. So we can just imagine TiCDC as a stream processing system, but for TiDB. And the resolve TS like a signal to tell the TiCDC that you can move forward. You can send the data to downstream, and it's okay. It's safe. So we use the resolve TS to advance the process of the table pipeline. Today, I'm not gonna cover how to calculate the resolve TS because it's too complicated. Maybe next time I can share with you. Mounter. Because the row KV is not easy to handle, we just receive a bunch of key values from TiKV. We have to use a schema info to convert it. We can't directly send a bunch of bits to the downstream. You can see they are just a bunch of bits and no other information. And you can see we have a value and the old value. We can just use a schema information to convert them into columns and pre-columns. This kind of row change structure is easy to handle for TiCDC. We can use it to to do the downstream data processing. For example, we can use this structure to generate the CQ statement or a Kafka message, and it will bring some column info and the table info, not just a bunch of bits. Sync. Finally, we got sync. We can send the data to MySQL or TiDB or Kafka. We can use the official MySQL driver to send the data to TiDB. It's very convenient because we have we haven't got other hack. We can just use the official driver to send data. And also we can use a Serama as a producer to produce the data to Kafka. Serama is a Golang library for produce the Kafka message. And we also have a S3 sync, but it's not ready yet. We will release it in the next version, maybe 6.5. Yeah, probably. There are some examples of real CQ or JSON data. We can see the CQ statement is easy to understand. We just reverse the row change into the CQ statement because we have a value and old value, so we can generate the updated statement. And the JSON data is also easy to understand. We use a Canal JSON format. This format developed by Alibaba, used by many Chinese companies. We can encode it to a Kafka message and send it to Kafka. And also it can be easily decoded by Flink or other data processing framework. So I think it's very convenient. Now you have know the data flow of TiCDC. It's a core of TiCDC. So let's check the data flow metrics because maybe you got some question or some on-call from users or customers. Then if you check the data flow metrics, you will know the throughput of TiCDC. As I said before, the throughput is a very important performance indicator to measure your whole system. And you can see this is a TiCDC Grafana dashboard. We can see the data flow metrics here. In Grafana dashboard, we call this collection as a row, Grafana row. So this row is for the TiCDC pipeline and for those 4 components. The first one is the puller. You can see here you can see there are 2 kinds of events. One is a KV event. The other one is a resolved event. The KV event is just data we received from TiKV. The resolved event is a watermark we received from TiKV to advance the TiCDC. If you found the KV event is too less and the resolve events is too much, it means you have a lot of region on TiKV because we calculate the resolve TS by region. So if there are too many resolve TS, it means that you got a lot of regions on TiKV. Maybe it will cause some problem, but I think it depends on your cluster on your cluster situation. The second one is the sorter. This one. We sort the data by community TS, and we output the data to the monitor and the sync. And you probably found not only the KV event, but also the resolve event is here. Because the sorter will output the resolve event to advance the whole pipeline. And the sync, we use the resolve TS to advance the sync. So we sort the KV event and the resolve event together. We also have a special role, special Grafana role for sorter because it's very important. You can check this one called unified sorter. Because if we can't write the data to the downstream immediately, we have to buffer the data. Because if your sync is too slow, you have to buffer the data in disk. So we have to measure the disk usage. If the disk usage is too high, it means probably your your sync is too slow. A bunch of data is waiting to send to the downstream. You should find a way to speed up your sync. And the third one is mounter. It's a simple one. We convert the row KV into row changes and send it to sync. So we just convert a bunch of key value to a bunch of row changes. So it's just you can see only the row changes. The last one is the sync. It's also very important for TiCDC. We can send the data to TiDB or Kafka. So we measure the received events and flash the events, because sometimes the data is not sent to the downstream immediately. We have to buffer it in sync or in memory. Like the data have some conflicts. We have to execute them one by one. So it will cause some delay. So we have two metrics to measure them. And we also have some special rows for sync, special Grafana rows for sync. Like we can send the data to a database or a Kafka. So we split into two parts. But we can check the general metrics here. You can see output row count panel. This panel is for it's the same as the flashed rows as above, like this one. It's the same one, and it means how many rows are sent to the downstream. You can see this metric. We sent about 25,000 to the downstream, and I think it's very fast. And also you can see the output DDL count and executing duration for the DDL. And another panel I wanted to mention is the large rows panel. There is no data for this panel, but it's very important, because if the large rows if your row is too large, it will cause a TiCDC report an error, such as if the row change bigger than the whole table memory quota, because we replicate the data by table, so we have to control the memory use. So we have a configuration or fixed memory quota for this whole pipeline. So if your row change bigger than this table memory quota, we can't send it. Also, in Kafka, we got some message size limitation. So maybe this large row cannot send to Kafka. So if you found some large row in this matrix, you should change your configuration to change your TiCDC configuration to send it to downstream. Otherwise, it will cause an error. And another rule for the sync is for the database. We call it a transition sync, because only in a database we have a transition. And in this rule, you could focus on two panels. The first one is conflict detect duration. It's very important. If you have too many rows conflicts, like using the one transition, it will cause we send it to downstream one by one, because we want to keep the consistency and keep the order. So it will cause a lot of delay. Sometimes it's related to your workload. It's related to your database schema. And the second one is the flash duration. If it's high, it probably means your downstream is too slow. So you should speed up the downstream. The last one is for Kafka. We call it MQ sync, because Kafka is a message queue. So it's similar to the transition sync. You need to focus on the duration. This one, work batch flash duration. there is no conflict detected in Kafka because we send the data to Kafka row by row, not like a translation or something. So there is no conflict. We just send it one by one. And this is all for the data flow. Now you have known the throughput of TiCDC because you know how many rows sent to the downstream. But how do you know the latency? Users probably saw a bunch of rows sent to the downstream, but they only care about the difference between the upstream and the downstream. There are several metrics to measure the latency. Also, those metrics indicate the latency for different parts of the data flow or TiCDC system. For the latency, you can focus on this row, this graph-analysis row. We have a lag analyze row. We can see the latency for different parts of TiCDC. The first metric is a checkpoint lag. It's a latency between the upstream and downstream. If you found the checkpoint lag is very big, it means the downstream and upstream are very far away. Maybe you have some problem in sync. Maybe the sync throughput is too low, and maybe there are too many conflicts in the sync. So you should find a way to locate the problem. The second one is resolve TS lag. It's an internal indicator. It's a very complicated metric. Also, it's not easy to explain and understand. You can think it's just the lag between the table's resolve TS and the current timestamp. We receive the resolve TS from TiKV, as I said before, but it's for each region. So we have to calculate the minimum resolve TS for the whole table because we send the data by table, not by region. We also use it. We also use this metrics for redo log and the sync point and the DDL, but it's really difficult to understand. So I'll pick the DDL to try to explain it and try to explain how we execute the DDL. DDL is a special event. We have to execute it one by one in owner. You can imagine if we execute the DDL on different capture, like a different instance of TiCDC, it will cause some conflicts. So we introduced a concept in TiCDC called global resolve TS. It's for all tables, just like a barrier. We use it to prevent other captures execute the DMLs before the DDL is executed. For example, if you have a DDL stuck in the owner, then the table's global resolve TS will be stuck, and other tables can't execute the DML because the DDL haven't executed. So probably your checkpoint TS lag and the resolve TS lag will increase because the DDL stuck. I guess you guys have a question. Actually, we can replicate the data for multiple tables. So how do we calculate the checkpoint TS and the resolve TS? Because it's maybe come from different tables. Actually, we use the slowest tables checkpoint TS and the resolve TS as the global checkpoint TS and the resolve TS. So we show this is a global checkpoint TS and this is a global resolve TS. So if you have a table stuck, it will cause the global checkpoint TS and the resolve TS stuck. And we added two panel for them to help you find the stuck table because you just saw the lag is increasing, but you don't know which table is stuck. So we have some metrics to find it. The first one is in this row called change field, and the first one is the mean resolve table ID. You can see the table ID here. Let me zoom in. Yeah, you can see that the table ID is 74, and if you found the metric looks like a straight line, like just a straight line, it means that the table is stuck. It's always the same table. You can use the table ID to find the root cause. We only have a table ID instead of table name because the table name may change, but the table ID will not change in same cluster. You can search the table name in the log by the table ID. Then you can find the stuck table. And the second one is the mean checkpoint TS table ID. It's similar to the mean resolved table ID metric. You can use it to find the root cause and find out which table is stuck. Okay, let's move on the frequently asked question. There are many questions about TiCDC, but we can divide them into two categories. First, people really care about latency. They always want a lower latency. Second, some people care about the technical details. They want to know why TiCDC is designed in this way, not in that way. So I'm gonna cover those two categories. Let's start with latency. There are many reasons for the high latency. Let's start with big transaction. If the big transaction, if your transaction is too big, it will take a long time to replicate it to the downstream, because we need to keep the order and keep the consistency. So we have to buffer it in sync and wait the whole big transaction is finished. So it will cause some big latency, because we have to wait the whole transaction. So we find a way to solve this problem. We can split the biggest transaction into small ones to get a better performance and a better control of the memory usage, because we have no need to keep it in the memory. But this feature is only available in version 6.1.0. And the second reason is throughput is too low. We can just increase the throughput by increase the table memory quota. This link for this configuration. As I said before, we replicate the data by table. So we need to control the memory usage of each table. This is a configuration for each table, not for whole training feed or whole cluster or capture. The default quota is 10 megabits. So I think it's quite small, not so big. You can increase it to get a high throughput if you have enough memory. I think it's very helpful for the throughput. You can also increase the sync worker count to get a higher throughput. This is a configuration for the sync. In TiCDC, we have multiple sync workers. We can send the data parallelly if there are no conflicts. So we can increase the sync worker count to get better performance, because more worker can send the data to the downstream at the same time. So maybe you will get a higher throughput. Also, the TiKV region count is also an important factor. If you have too many regions, it will cause the TiCDC spends too much time to deal with the result TS, because we receive the result TS from each region, and we spend a lot of CPU to deal with the result TS. Then we can't deal with the key value event, the real change. And probably it's also cause a big latency. For now, we can't solve the problem, but we will improve it in the future. Also, if your workload is too high on the upstream, it will cause a big latency, because maybe just TiCDC can't catch up the upstream. The workload is too big for TiCDC. There are also some upstream issues. For example, the region leader transfer. If the region leader transfer happens too frequently, it probably causes a big latency because TiCDC needs to reconnect to the new leader and try to get the result TS from this new leader. So if the result TS cannot advance, it will cause a big latency because the whole pipeline cannot advance. Sometimes if your TiDB cluster is crashed, it probably causes a big latency because before the crash, it may leave some locks on the TiKV, and the result TS cannot advance because of those locks. If the locks exist for a long time, it will cause a big latency. But TiCDC try to resolve the locks if it can. There are also some downstream issues. For example, if the downstream database is too slow, it will cause a big latency because TiCDC cannot send the data to the downstream at a high speed. Also, if there are too many write conflicts, probably it will cause a big latency. You can imagine TiCDC will retry the write option again and again. You can imagine if you use the TiCDC to replicate the data, and at the same time, you have some workload on the downstream. Maybe they will write the same table, So it causes a lot of conflicts. So TiCDC maybe needs to retry it again and again. It causes a big delay. The last reason is cluster topology. If you deploy TiCDC in a cross-region deployment, you should consider the network issue. We need to keep low latency between the upstream and the downstream. I guess sometimes putting the TiCDC in the same region with the downstream is a good choice. It helps to reduce replication latency. It's most of the reason for the latency. Let's move on the technical details. There are several technical details. A lot of users argue about the design of TiCDC, so I'm gonna cover them. Let's start with the data replication method. We can use a raft learner to replicate the data, or we can use the raft log event. We choose the later one. Because as I said before, we need to consider the data integration and also provide a different consistency guarantees. So we can't simply use a raft learner. Also, if you want to send the data to Kafka, you still have to deal with the schema info and convert the ROKV. Because if you use a raft learner, you have to convert the ROKV to the Kafka message. I think you can't just send the ROKV data to Kafka. And I guess there are no big performance difference between those two methods. So we choose the raft log event. And second, about the data order. Many people care about the data order, but many people don't. So recently we are discussing whether we should keep the data order by default, because now we want to keep the data order for Kafka or MySQL. Actually, some users use Kafka. They don't care about the data order because maybe they reorder the data by themselves. So maybe we can just make it optional in the future. And about the ret method, we choose the CQ method because it's easy to extend. For example, we can replicate the data to any MySQL compatible database. So we choose a CQ method instead of real KV method. I guess it's more flexible. And the last question is about scalability. Actually, maybe you have a question. Why we schedule the tables based on the table count, not the workload? Because as you can see, we replicate the data by table. The whole pipeline for table. So we simply schedule the tables based on the table count. It's easy to understand and it's easy to implement. But sometimes we suffer from the uneven workload. For example, if we have a big table and a small table on the same capture, on the same node, the big table or hot table will occupy most of the resource, and the TiCDC treats them equally. I think it's not fair, and also it's not make sense. So we are discussing how to improve it in the future. Maybe we can schedule the tables based on the workload. It's more reasonable, and but it's not easy to implement. So we are still discussing it. Maybe we can split the table and replicate the table on different TiCDC instance, not just one pipeline for one table, and only can send the table for the only one instance. Maybe we can just split it by some range or something. It's also a good choice, but it's extremely hard to implement because we need to handle the region merge and region split in TiCDC. So please stay tuned. We will improve it in the future. Okay, thanks for your listening. Let's move on the Q&A session. Do you have any question?
Yes, thank you. Thank you, Rustin, for your great sharing. And I also found that plenty of questions are raised by the chat box. So okay. Let's start from the first one. Yeah. So Daniel Liu asked, how does TiCDC fetch data from the source TiKV nodes? And I think Yubo has answered this, said push the raster log in the TiKV node to the CDC node. So it's like yes. Push data from the TiKV to CDC, right?
Yeah, and I also think that this was answered later in the presentation.
Yes. Okay. So next one is about Daniel, you can ask if it's still not answered.
That's about setting up TiDB to TiDB replication with TiCDC. Is it correct that requires you to first restore a backup of the source cluster, or does TiCDC have the ability to use BR and Lightning to make sure that the initial data gets replicated?
I get it. Thank you for your question. I think it's a great question because many users confusing about those tools because we got lots of tools. And for now, I think we have to use BR, backup restore, or Lightning to do a recover, and then you can use TiCDC because TiCDC only for the incremental data, not the full data. So I think it's for now we have to use the BR or Lightning to recover the data from the upstream, and then you can pick a timestamp to use the TiCDC to replicate the incremental data.
Yeah, the reason I'm asking is that if you use DM, data migration, then data migration can use, I think, dumpling and Lightning to do the initial replication.
I think it's more like a product decision, not a technical decision, because it's maybe it's easy to integration with BR or Lightning, but I guess it's a product decision. Maybe you can ask our product manager because it's hard to it's hard to say. Should we just integration with the integrate the BR and letting into TiCDC? Yeah.
Yeah. So if we would do this, this could make it easier for people to use TiCDC, because then they don't have to specify like a timestamp, etc. And I think one of the concerns that people have with TiCDC is that it's sometimes quite complex to set up.
Yeah, I think it makes sense, but I guess if we use a TiDB cloud, maybe we can just maybe we can just combine those tools as a service, and maybe it will help for this situation. Yeah.
Yes, thank you.
Yeah, cool. So yeah, I saw Alan is also here. Yeah, so maybe this is also a future backlog for improve our products. Yeah, thanks, Daniel, for your. Yeah, Alan, do you want to say something?
Yeah. Well, actually, here there are some customer, they want that TiCDC can, do the data initialize when, we are doing TiCDC to TiCDC data replication, and we will, will consider it in the future releases. Yeah.
Yeah. Okay. Thank you.
Yeah. Thank you.
Yeah. So let's go to the next question. What about the relation between TiCDC and the TiKV CDC? So this is also listed by Daniel.
Yeah, I can answer this question. It's I think it's different, because the TiCDC more like for the transition key value in TiKV, not TiCDC, like as I said before, we have to keep some consistency, so we have to deal with translation concept, not just a root KV. And I think TiKV CDC only for root KV, not the translation KV. So I think it's a really different. Yeah.
Yeah. Okay. Yeah, maybe different product value propositioning for different usage. Yeah.
Yeah. I guess the TiKV CDC always for TiKV, not for like a TiDB to TiDB. It's more like a TiKV to TiKV.
Yes. Yeah. Next is raised by Zhen. He asked where the CDC consolidates the metadata, such as checkpoint, task property, etc.
Yeah. A good question. Because I missed this part from my talk, because it's involves the PD. Actually, we store the metadata and checkpoint TS and the result TS and the task position in PD. So also we use a PD to elect our owner and our leader. So we use a PD, and we just store the data in the etcd.
Yeah, thanks. Next one is from Li Jia. Li Jia asks, does the processor have any queue mechanism?
Yeah,
I think
sorry.
that is going to it's want to ask how we guarantee the data consistency or transaction consistency, I think. Yeah, Li Jia, do you?
Yeah. So because most of the time is we cannot control the speed to write into the sink. So there will be cases that when there's large transactions or etc., it will be queued, like you said, in memory. So it will, if we want to persist the data in case of replication data loss or whatsoever. So some other products implemented the queue mechanism like Kafka in the TiCDC. So that,
Yeah, I get it. Yeah, actually, we have a queen for the data, but not like for the whole processor, but only for one table, because we replicate the data by table. So we have a sorter, and we can use the sorter to buffer the data before we send it to the downstream. We can buffer it on the desk, and because sorter keeps the order, so we can just we can just so sync can get the data from sorter one by one and send it. If there is no enough memory, or there is some different between the upstream and downstream, we have to keep it in the disk. Then we will keep them in sorter and just get it from sorter if we wanna just keep the replicating. Yeah.
Okay. Thanks.
Yeah, thanks. So next, it's asking that what are the limitations between bidirectional replication? I think this still under development, right? We do not have bidirectional replication now, from my understanding.
Yeah. You are right. We only, we haven't get that replication. Yeah.
Yeah. So, do you see any limitation or something difficult for us to achieve this for now?
I guess it's difficult to like change the whole design of TiCDC to support it. Yeah.
Okay.
It's because for now we replicate the data by table, so it's really difficult to just split it or schedule the table by regions or something. Yeah.
Okay, yeah. So yeah, actually this feature has been required by another lighthouse in APAC. So I think it's in under development, and yeah, it will soon to be delivered, maybe the end of this year. So maybe like that time, let's see how it is. Yeah. Okay, so next question is when start TiCDC to apply a large and long-running transaction once it has fully committed? Oh, yes, I think.
Yeah. I think it's I guess it's not related to the long-running transition, because we only get the data after the TiDB committed, or we only execute it when the transition is committed. So maybe we can just get the data, but keep it in the memory or something. But for a big transition or large transition, we have to keep it in memory. Like if you have maybe 400,000 rows in one transition, we will keep with the whole transition is finished. We will start a transition and execute these rows one by one and committed this one transition like you committed as on the TiDB. So it's a fully committed. Yeah.
Yeah. Daniel, do you have some further questions on this?
No, that fully answers the question.
Yeah, thank you. Yeah. So next two, I think it's like a feature requirement from Daniel in APAC, also in email. That's ask, are there any plans to support the how to say that, DB Zoom formats?
DB Zoom.
Yeah.
I guess DB Zoom. Yeah.
Yeah.
I guess DB Zoom is more like a platform or framework. So actually, I guess DB Zoom can use Avro to process the data. But so we can just use Avro. Maybe I messed up the DB Zoom, but I guess maybe we can. Oh, I know the DB zone use MySQL binlog, right?
Yes, but DBSum in production has lots of bugs, so I don't understand why customers will use DBSum.
Yeah. I guess it's difficult to integrate with DBSum because I remember the DBSum use MySQL binlog, not. I don't know how to integrate it. Yeah.
I think the question here is to support the format that the BCM sends to Kafka, because people might have things that are already now consuming things that are the format that the BCM is sending, and then switching from the BCM to TiCDC would be easier.
Yeah, I get the question. I guess you can just use Avro. If the DBSum have a good support for Kafka, I guess maybe we can just use Avro, and maybe some like a TiDBC connector for Kafka also can help for this problem, I guess. But I don't know. Actually, I'm not very familiar with the DBSum, so it's hard to answer the question. Yeah.
Yes, no worry, because I think it's more like a feature request. So if a customer have this feature request, you can raise in FRM. Then maybe Alan or Lan here can have a detailed look into it and then decide whether we will support this yes or not in future. Yeah. So yeah. So let's move on. Next, I think is a suggestion from Daniel. Could you please, for data order, could you please have some explanation for that?
Yeah, this is was just a remark about the slide that had things about not supporting the exact data order. So in MySQL, there are also options to not have a very strict data order, but still have consistency between transactions. So there are a few links there, etc.
Yeah, thank you for your sharing.
Yeah, okay. I think later I will also collect all the feedback in one doc and then send it to you. I think it's both helpful for not only for frontline and also for our product and the development team. Yeah, thank you, Daniel. Yeah. So next is I think it's from Elvin and it's answered by Sean as well. The next one, it's is there any plans to create a tie-up playground with TiCDC? Okay, yeah, it's maybe also a feature request that is not really is that very related to CDC or more related to tie-up team?
Yeah, actually we have this function in tab. You can just tab playground 刚刚TiCDC and give the number of the TiCDC instance. We can stop the TiCDC cluster. I think it's already in tab.
Okay, yeah. So later maybe you can share some guides. Yeah. I will pass it into the doc and share to the front line as well. Yeah. And the next is from Jen. He asked whether our DDL statements will block all the progress, no matter the transaction related to the table involved by the DDL statements.
Yes, I think the answer is yes, because we have to as I said before, we calculated the checkpoint as a global checkpoint TS and a global resolved TS, and this resolved TS maybe comes from DDL. If your DDL cannot execute, so it will block other DMLs maybe before or after this DDL. If this DDL comes from the slowest table, it will block the whole block the whole class, block the whole change feed. Other table can't make progress because of DDL. So I think this is a problem. Maybe we can solve it in the future.
Okay, got it. Thanks.
Yeah, cool. And I also say Alan also have the command line to help you know how to use tie-up to run TiCDC, right? Yeah. Thank you, Alan. So yeah, is there any further question? You can yeah, you can open your microphone. Yeah. Yeah, if no, yeah, thank you very much. Thank you, Rustin, for your great sharing and also for this Q&A session. And also very thank you for everyone to attend this session. I will send this this recording to your email later. Yeah, yeah. So sounds good. Yeah. Thank you, everyone. So let's close today's session. Yeah. Have a nice weekend.
Thanks for organizing this.